Hey guys, I'm gonna go over the potential energy quote unquote quiz, potential energy diagram quiz that's due today. So here we go. I'll take a picture. I'll do my normal thing here so I can write on this. Actually, here, let's do it this way. That's good enough. All right. So, all right. Before I go over the actual individual answers, I'm just going to kind of label this thing here. So, let's see. We'll stick with that color. All right. So, A and E are something I haven't talked about yet. If Y is your energy, potential energy, or the amount of energy involved with this curve, and these are your reactants, right? So here's your reactants and here's your products. E represents the energy of the products. Let me give you an example of that. Well, here, hold on. And then A represents the energy of the reactants. And what that means, the potential energy, and you can see that the reactants have more energy than the product. So again, let's say this is 0 and let's say this is 100. So let's say maybe this is 75, right? The reactants, and let's say it's kilojoules, kJ, and then the products have, let's say, 25, okay? So the reactants have more energy than the product. What does that mean? Well, think about food. If you eat a steak, okay? All right, so if you eat a steak, let's say it contains, I don't know, I could take a guess, 2,000 joules of energy. Whereas a banana, I know a banana, like a average medium-sized banana, I want to say is around 400 joules. Something like that. All right, and again, steak sizes 8 ounce, 12 ounce, whatever. Forget all that for now. The point is, you eat something like a steak, it has a ton of energy in it, potential. When you eat it, you can get energy from that. A banana doesn't have as much. Beans have a high energy content. Chickpeas, garbanzo beans, for example, soybeans, lots of energy. Other beans have energy too, not as much as those two, but anyways, that's what I mean by potential energy here. So I know I'm relating like a chemical reaction to food, which is strange. I'm just helping you understand the concept here, that I think you get, steak has more calories, banana has less calories. Calories, people get obsessed with calories and weight, and all that is not really a healthy way to look at it. Really, calories is just energy. How much energy are you getting out of the food? So anyways, that's what this is about. So from the 0 up to the reactants, A, that's how much energy, potential energy, stored in the chemical bonds of the reactants. Then from 0 up to P, that's how much potential energy is stored in the products. Okay, let me clear that. Okay, so B is from the reactants to the top of the peak. So B is our activation energy. That's what that is. The energy needed to get to the top so it can start colliding. All right, right at the very top, that's your activated complex. So that is where your X should be, right at the top. Letter C here is the activation energy of the reverse. So if going from the reactants up to the top is the activation energy of the forward, that's how much energy is needed to give the reactants. I don't know if I worded that right, but that's the amount of energy need to be given to the reactants to get to the top to start doing effective collisions with the proper orientation and all the stuff we talked about. And that's going from left to right. That's the forward reaction. Well, a lot of reactions are reversible, so we can go backwards, which is actually equilibrium, which is what we'll start talking about tomorrow. But if you want to go from here up to the top of the curve, which is C, that is the activation energy for the reverse reaction. So you want to start as a product and go back to being a reactant. So that's letter C. And then letter D is probably the most important, especially those of you taking AP Chem. So this is your delta H. So again, let's say this was 25 kilojoules, and then my reactants was 75. My delta H would be negative 50 kilojoules. Because we started as reactants with 75, we reacted, ended up down here as products, and we lost 50 kilojoules as we reacted. So that means it would be an exothermic reaction. Energy is released. And what does that mean? It means my products are much more stable than my reactants. Okay, less energy in chemistry means more stable. All right, so I kind of just answered a whole bunch of things there. And I know this reaction down here is represented by this. I was just making up numbers and just kind of going over some things we've been talking about, right? So I understand it. All right, here we go. So number one, activation energy of the forward. So that was B. 2, which potential energy diagram? Activation of reverse. That was C. So I just went over that. Heat of reaction would be D. That's the difference in energy between my reactants and my products. Which represents the reactants, which potential energy interval. So A is reactants. E are products. That's not worded too well, but X where activated complex would be right at the top. What is the value of the heat of reaction? So the value is right here. And it's negative 890.4. We learned a long time ago that kind of, I use class as an example. When class starts, you enter the room. So endo means it's in the beginning. Endo, the energy is in the beginning over here. Exo, like this reaction, exothermic, you exit the room at the end of class, right? So at the end, you release, you exit that energy. So that's 890.4. The only thing is this isn't really a plus sign. It just means it's part of the products. So kind of. So the value is actually negative 890.4. That negative meaning it's being released, right? So energy isn't negative. All right, there is no positive negative energy, right? So the energy in a banana or a steak or beans or whatever, whatever food you want to talk about, there isn't negative energy. Energy just is. It's something you can measure, and there is no positive or negative. So the negative just represents losing, right? Releasing that energy. So that's negative 890.4 for letters or number 7. Okay, 8. It is exothermic, and why you would say the products have less energy than the reactants. I know I'm abbreviating. Products have less energy than reactants. That means, that means energy was lost as the reaction progressed. I'm kind of out of room there. Okay. Let me clear this. 9. Explain in terms of collision theory why a lower concentration of oxygen gas decreases the rate of this reaction. So when we look up here, it wants to know why if we have a lower concentration of oxygen, it decreases the rate, meaning it reacts slower. That's what that means. It reacts slower. And here's why. In terms, right, collisions. Okay. So basically what we have here, we have CH4 and O2, right? So if I draw CH4, so here's CH4. There's CH4. And let me draw O2. I'll use a different color. Those are kind of two ugly colors to mix. Whatever. Here we go. We'll do this one. Okay, so now here's O2. These have to collide with each other, right? So this one's got to go this way. This one's got to go this way. They need to collide, and they need to have proper energy, sufficient energy, and proper orientation. If they do that correctly, then they will make CO2 and water, release energy, and the reaction will progress. So basically what this question is saying is, number 9 here, is if you decrease the amount of O2, right? So you want to burn methane, but you only have a little tiny bit of oxygen, you're not really going to get a whole lot of reactions. Why? Because you don't have the number of particles necessary to have effective collisions. The more particles you have, the more collisions occur, the faster the reaction will occur. If you decrease the number of particles, you're decreasing the collisions, right? So sometimes with collisions, I use the analogy of bouncy balls. So if we cleared our room at school and it was just empty room and we all were holding one bouncy ball and we just spiked them in the ground together, yeah, some of them might collide. But what if we were each holding 20 bouncy balls and we spiked them in the ground all at the same time? If we're each providing 20 particles versus one, there's going to be many or much more collisions with the 20 bouncy balls, right? So the more balls we spike into the ground, the more times they're going to collide with each other. And that the analogy is there will be more reactions, right? More products. So that's the answer number 9. That if you decrease the number of oxygen particles, there will be a decrease in the number of collisions. Therefore, decrease in the rate of the reaction. I know I didn't write that, but if you're watching this, you should be able to stay with me there. So again, I guess I can kind of try and squeeze it in here. Why? So if we decrease the number of O2 particles, right? That's decreasing concentration means less particles. Then that decreases the number of effective collisions, which equals a decrease in reaction rate, right? So the collisions won't happen as often because there's less particles, meaning they won't form products as often, so everything's going to slow down. Okay. All right. 10. You know what? Let me take a new picture. All right, let me do that, and then I'll just zoom in here. Okay, so number 10, using table I in the space provided, draw a potential energy diagram for the following reaction. All right, so I think what I'll do is I'll do this here. H2 plus I2 yields 2HI. All right, now I'm going to go to the interwebs here. Reference table I, here we go. All right, so where are we? Down here. Here it is. H2 plus I2 yields 2HI, positive 53. It's endothermic. That's all I need to know. So the 53 would go over here. It's endothermic. So what I wanted to see from you guys is an endothermic curve. This is endothermic. My H2 plus I2 here. My HI would be here. It gained energy, right? Here's potential energy. And the difference between these two would be positive 53, which is my delta H. Positive 53 kilojoules. I'm leaving off units, but whatever. So there it is. That's what I needed to see. Your products are higher than your reactants. Endothermic. Okay. Show how the catalyst will change from number 10. All right, so let me clear that. All right, so if this is what you drew, something like this, catalyst would be a dotted line underneath. You would just have to make sure that your dotted line ended and started here and here. So your products and reactants, you cannot have the dotted line go underneath, or it can't end too soon or start too late. So let me erase that here. Or you know what? Let me do this. Oh boy. Okay. Let me start over. So here, you know what I'll do? I'll do a solid look because there's some things I want to show you here. So basically, if you do this, you get, see, that actually would be, you would lose points. So I did that too quick. So you have to start at your reactants and end at your products. You can't stop above or below that product line because the delta H, the difference between these two, stays the same. That never changes. It just creates products faster when you take that alternative pathway. So this is something hard to do remotely. I'd have to look at all your answers and then give individual feedback. It's easier in class, obviously, to do that. So But anyways, I'm hoping with these videos and in class when I go over work that you're doing just what we do in school. You're looking at what you did based on what I say the answers are, and you're seeing where you did things right, wrong, and then figuring it out. So that's how a catalyst needs to be drawn. Okay. How does a catalyst increase? Be specific. Okay. So how does a catalyst increase the rate of reaction? So it decreases that activation energy. Decreases activation energy. That's it. It brings down that peak. So instead of the reactants having to go all the way to the top of this mountain, they take a shortcut and go to the top of this one. So it's a lot less energy needed, so it reacts faster. What is the value of that for question 10? It's the same. So if this is positive 53, wait, over here. If this is 53 kilojoules, 53.0, this is gaining 53 to react. Whether you use the catalyst or not, it's still positive 53 kilojoules, right? So if you go back here, and again, last thing, then I'll stop. I know this is kind of a long video. So again, here we go. So here's my reaction. So here's my delta H between here and here. There's my delta H, which is positive 53 kilojoules. Here's my products. Here's my reactants. Whether you take the long original path or you take the catalyst, the shortcut, the alternate pathway with a lower activation energy, it doesn't matter. The difference between P and R is still positive 53. Delta H has never changed, whether you use a catalyst or not, it doesn't matter. Again, the steak and the banana, right? The steak and the banana, if you eat it slow or you eat it fast, it doesn't matter. It's the same amount of energy, right? So think of it that way too. So it doesn't matter. All right, that was a long video, but I really wanted to go over that kind of carefully. So there it is. I'll see you guys tomorrow.